In the next section, we'll continue where we left off with dealing with gaseous oxygen. So we started talking about oxygen cylinders, and the most common you'll see out there today is the DOT-3AL, which is an aluminum cylinder, but it's wrapped with a fiberglass winding. Even though the rated pressure on these is over 2200 psi, typically they're run at about 1800, 1850. They do have to be removed from the aircraft and hydrostatic tested every 5 years, but one of the advantages with this type is that they have an unlimited service life. So they as long as they pass inspection, they don't have any visible damage, as long as they pass required hydrostatic test, then they can continue on after that. That's compared to the various steel or composite bottles that have limited service life, or you can see the DOT-3HT, which actually has to track fillings, which is a particularly tough thing to do. So it has the advantage there. Now you can see that the DOT-3AA, 3AA is similar with limited life, but it's a much heavier bottle. These aluminum DOT-3ALs are actually quite lightweight given their size as well, and so they tend to have a pretty broad range of advantages and have made them the main bottle that you'll see out in the wild today. Next section we're going to look at is getting into, as part of the gaseous system, we have to regulate the flow of oxygen, and so there's a couple different types of functions that they can do. We'll get into masks and how regulators play into each other after we talk about the different types of systems here in a minute. But generally speaking, oxygen regulators are taking that high pressure, that 1800 psi or 1850 psi, and bringing it down to a pressure that's more that's at a level where it makes sense, or where it's useful for breathing. So we store it under high pressure, and then we can do a low volume under low pressure when we're actually using it. And these can be either continuous, where the oxygen's always flowing, or what's called demand. And in the case of demand, is there's a part of the regulator has a sensing function that as the user breathes in, the pressure downstream of the regulator on the mask side drops, and that's what allows oxygen to flow. And then when the user breathes back out again or stops breathing in, that pressure increases and the supply or the flow of oxygen is stopped. And it reduces the waste so that but makes the bottle and the amount of oxygen last longer over time. The next type of oxygen system is continuous flow, and so we can have continuous flow gaseous, but the most common continuous flow systems are going to be the ones used for the passengers. And you can see here in a cabin with the oxygen masks hanging down, the rubber jungle as it's sometimes referred to in the industry. These are what's called a rebreather type mask, and so a small amount of oxygen flows through the tube into the bag, and then when the user breathes in, they pull a mix of oxygen and ambient air into the cup mask, and then when they breathe out, it gets breathed out and comes out a little check valve in the back of the mask that you can see. You can kind of see it here, this little circle. These are the ones where famously when flight attendants talking about them, they say the bag may not inflate. Typically, it's not going to inflate during use. Sometimes when breathing out, it'll inflate, but that bag allows air, breathed out air, and oxygen to kind of mix back together, replacing the oxygen that then gets breathed in. These are based on chemical generators, so passenger service units known as PSUs. Those are the things that most people recognize because they have the air vents known as gaspers, as well as the lights and the flight attendant call buttons and those kind of things. Up on the back side of them is where the oxygen magic happens. And so if we look at this one here, kind of in the similar manner, here are the lights on the right, and then here are the air vents kind of in the middle. And then on the left, this is our oxygen system. So here is the mask stowage box, and then the release mechanism down below it. And then over here on the left, the oxygen generator. And then this little, the circular thing to the left is the speaker for the PA system. So these masks are inside of a door, maybe such as this one here. And when they're needed, that door opens, the masks are allowed to drop. And then the users, when the masks come down, when you pull on them, there's a string running from each mask to the firing pin on the oxygen generator. So right here is the firing pin, and there's a piece of string running from the masks to this firing pin. And so by pulling those, it releases this firing pin, and then the firing pin sets off the flow. What's not shown, what's hard to see here, just because of the way this picture cuts off, is the tubes, the actual oxygen tubes come in from the other side and are right here and go to the masks. So these oxygen generators look something like this. Here's that picture of them. Again, it's activated by a firing pin that's connected to the mask, shown here on kind of the top right. On the example schematic diagram, it's shown here on the top. And then the masks hook up on the opposite end of the little outlets. On the actual one here, shown on the bottom left, and on the schematic, it's at the bottom here. And so those are going to, that's where the mask hooked out. And then inside is a sodium, what's called a sodium chlorate candle. And so sodium chlorate, when it burns, it's one of the byproducts is it's going to releases oxygen, and that oxygen is allowed to flow out to the masks. Process of doing that, it does generate a significant amount of heat, several hundred degrees. And so these do get hot. You can see the one there, the label does say hot on it as a warning if it's been activated. And so we just got to keep that in mind when they're installed in their boxes. They're kind of in an area where hopefully they're not gonna damage, where it's designed where they won't damage anything. They're in kind of a metal bracket with airspace around them so that they don't damage anything. But these can be activated either automatically or manually. So up in the flight deck, there's a passenger oxygen controller, and that has a pressure sensor on it. And so if that senses a drop in cabin pressure, it can automatically open all those doors that allow the masks to drop to the passengers, or they all have a button that the crew can press if either it doesn't automatically deploy, or if they need to, say, deploy the masks in anticipation of having to open like the dump valve to clear the cabin or something like that. That ability does exist. It's also used by maintenance during testing. And one little thing with these, one kind of note is on these, the little door that opens, somewhere on this door, there's going to be a little kind of flag you can flip down along the edge. And that actually deactivates the door from being able to open all the way. It allows the latch to disengage, it allows the door to drop down a little bit, but it doesn't fully drop. And we can use that to test the door release without actually dropping all the masks and having to repack them. If we have a gaseous continuous flow, so in addition to chemical continuous flow, we can have gaseous continuous flow. Those use the same kind of oxygen cylinders we talked about earlier with gaseous systems. But in a case where they are plumbed typically to the kind of yellow cup masks, and when they're turned on, they flow continuously. They don't have any kind of a demand system. Gaseous continuous flow like this are most often installed in smaller aircraft that are used when they're at limited times above 10,000 feet, but not for a significant amount of time. That's in contrast to the chemical generators that only last a small amount of time. But the chemical generators are designed for an emergency situation where the aircraft is trying to ascend to a safe altitude as quickly as possible. So most of our crew oxygen systems are demand-based, and so that's where I alluded to earlier with the regulators. A demand oxygen system, in order to make them last longer, we have we don't run the oxygen consistently. We only run it when the user is actually breathing in. And so when that regulator senses a drop in downstream pressure, it allows oxygen to flow. And then when that individual stops breathing in and that pressure rises back up, the regulator cuts off the flow for a short period of time until the next inhalation. And that's in order to make it last longer and not have to have as big of an oxygen bottle and source. Demand systems can run in two modes. The most common is what's called diluter demand. And that is when the user is breathing in, they're not just breathing in the pure oxygen, but they're actually, the mask is pulling in some of the surrounding atmospheric air. And then it's simply just enriching the oxygen in the process. And so at the end of the day, there's nothing wrong with the air being thinner. It's just the oxygen content, in that thin air, there's just less oxygen available. So we can take thin air and put a bunch of oxygen into it and dilute it with oxygen. And it'll provide plenty of oxygen to the body to survive. So diluter demand, again, that allows for even longer, stretching that effective time even longer, because most of what's being breathed in and out is just nitrogen and other gases from the atmosphere, with a little bit of oxygen from the oxygen system being mixed in order to supplement the low oxygen in the thin atmosphere. Pressure demand is where we no longer dilute it. So it's pure oxygen, where when somebody breathes in, when they breathe in, that demand system allows oxygen to flow, but it's no longer diluted. You're just breathing pure oxygen. This may be the case where biggest thing is if for some reason the atmosphere surrounding the atmosphere surrounding the individual, such as if there's like smoke or chemical vapor in the air, we don't want that being mixed in and being breathed back in, and so we can go to pure oxygen pressure demand, but still last for a period of time. And then the third one is pressure mode, and pure or continuous flow. It's another name for a pressure mode or continuous flow, and in this case, a higher pressure is sent to the mask in order to make sure that smoke and chemical can't get in. And so it's often used just temporarily when the mask is first put on. If there is smoke or chemical vapor, the mask is just put on, you run pressure mode to purge out any of that contaminated air, and then often would switch over to pressure demand, only pulling oxygen in, breathing in. However, if that period of time where you're not breathing in is allowing smoke or those other things to kind of seep into the mask, then you can go back to the pressurized mode, back to a continuous flow mode where there's always a positive pressure inside the mask, and that'll keep anything from getting into it. So the demand, the regulator is what determines all this. And there's typically a regulator. There's always a regulator at the bottle itself, which brings the pressure down from that 1800 psi to something more manageable for the lines running throughout the aircraft, 40 or 50 psi. And then then there's a second regulator at the mask itself that is determining these different modes and setting the amount of pressure that the oxygen is being delivered under to the crew. So crew masks can be switched between these modes in almost any crew mask that's out there. But again, these are crew only. These aren't used for the passengers. The idea being that the crew needs to maintain the ability to fly the aircraft, to maintain cognitive ability. The passengers, really the kind of the thin, flimsy yellow masks are just enough to keep them alive until the crew can get the aircraft down to a lower altitude after some kind of an event where pressurization is lost. So here's those masks, the quick donning masks here on the right, and I showed the video in class for this, but where they can be diluter demand, pressure demand. They can be some kind of a combination. And the regulator on them in front of the nose area, that's what allows the crew to quickly change. So we got, here's kind of two types of quick downing mask, the hose style on the right. And the mask on the left uses a little bit different setup, kind of a frame that goes around. It's a little bit bulkier. Most of those on new aircraft have been replaced by the hose style that fits in a smaller compartment. In addition to the fixed oxygen systems on the aircraft, they're going to have portable oxygen as well. And these are just simply a portable oxygen bottle. There's a regulator at the top of it with a valve to turn on and off. And then that's connected to, in the yellow pouch, one or two, usually two oxygen masks that can be used by the crew, the cabin crew, during an emergency. And then the carrying, with a strap to be able to carry it. And so cabin crew are going to use these. Most cabin crew are going to have they're going to have a fixed chemical oxygen generator over their jump seats that you would normally sit in. But in the event of an emergency like that, oftentimes they'll need to move around the cabin, especially if there's some kind of preparation taking place for an emergency landing. And so these bottles will be available near the flight attendant stations and overhead bins at the ends of the cabin that they can grab, kind of put the strap over their shoulder and have a mask and be able to walk around, move around the cabin. The other area that these bottles are used is for medical emergencies. So if a passenger has a medical emergency, these can be brought out and used as medical oxygen in addition to other emergency medical supplies that are kept on the aircraft. So kind of a dual purpose here with the portable oxygen bottles. And these are also serviced to about 1850 PSI. We had adapters where the same carts we would use to service the oxygen on the aircraft, the installed systems, we could use to refill these. And they follow a lot of the same DOT regulations, the DOT-3AL regulations, that the bottles that are actually installed in the aircraft. These are just smaller. So the maintenance side of things, oxygen servicing is covered in ATA Chapter 12. As I've talked about, most of these systems at normal temperatures are somewhere around 1800 to 2000 PSI. And so when we're working with these, we want to make sure that we're clean, that we don't create a fire hazard or a safety or a health hazard by contaminating the system. Part of that too is after the system's been worked on, if any lines have been disconnected, hoses, pipes, we need to run some oxygen through the system in order to purge out any gas that got in there, nitrogen, mainly air, what's in the air. And so that's just a matter of having the bottles activated, and then going to the oxygen masks and allowing air to run through the gaseous system. Oxygen masks, putting them on continuous flow and purging oxygen through, to make sure we push any air or other gases out of the system. The other part of that is once we've done that and we've shut everything off, now the bottle itself, the oxygen bottle on the aircraft is left on so that it can flow to the system when needed. But we want to make sure that there aren't any leaks in the system. One is so that the oxygen's available when it's needed. The other is we don't want to create a fire hazard. And so we need to go around and apply leak check solution. Basically, it's kind of like a soapy water on the various connections to make sure that there's no bubbles that form and ensure that the system is leak checked. And once we've done all that, then we want to recheck the service and make sure we put it at the proper system charge, proper level. And so that will vary based on ambient temperature and bottle temperature. And so here's kind of a general oxygen servicing chart. So you can see at the 50 to 60 degree range, that's where we're in the 1800s. You can see the filling pressure that it's talking about here is the minimum pressure that's in the bottle that we're using to fill our system, but then the system pressure at 70 psi, once it settles out, it needs to be either 1800 or 1850 psi. Part of this, the reason these numbers are higher is that during the process of filling the oxygen system, the bottle temperature actually increases. So as we're forcing air into the bottle on the aircraft, that's going to increase the temperature of the bottle on the aircraft. So that bottle is actually going to be a little bit warmer than what the ambient temperature is. So kind of what this chart is saying is, say at 70 degrees, if we're trying to get 1850 psi, we would service the bottle to 1975 because just the act of filling it is going to cause it to run higher. And so these systems are designed to be slightly over serviced during the process of servicing to make up for the fact that they heat up or they warm up during servicing. I talked about purging a minute ago, and so here's just kind of restating that, allow pressure to flow through the system. And this is done anytime the pressurized portion of the system has been opened and then reclosed. And then here is that leak check solution. The most common I've seen out there brand-wise is called Sherlock, and it's a low bubble, it's non-flammable. Essentially, it's fancy soapy water. And but it's been certified as non-toxic and can be used around oxygen systems and all that. We would also this kind of stuff can also be used for things like checking uh, valves on the servicing ports and other things for accumulators and struts and all that. It's basically any kind of gas that is under pressure where you want to make sure there isn't a leak. You can use this Sherlock compound in order to leak check it.